our time. Who am I missing? One person I'm missing. Nick. Okay. Right. Where is my chat box? So yesterday we looked at the electrophilic substitution, and you saw that the delocalized electrons, a pair of electrons is being donated to an electrophile. If you see this, my arrow is cutting through bond carbon number 1 and carbon number 2. So if you draw it like this, that means your electrophile can either sit on carbon 1 or 2 only. Okay. If you want to make your electrophile sit on carbon number 5, you would draw an arrow like this. Okay. So the one in your notes, they have put the electrophile on carbon number 1, which is fitting because wherever your electrophile sits after that becomes automatically carbon number 1. Even though in your benzene ring you don't see the hydrogen, because it is a skeletal formula, there should be a hydrogen on each carbon. Okay, when the delocalized electrons has already been donated to the electrophile sits on the first carbon. The delocalized system is broken. Okay. Since electrophile sits on carbon number 1, delocalization only extends from carbon number 2 to carbon number 6, okay, with a positive charge. And to restore the delocalization, electron has to come from the carbon-hydrogen bond to be donated to the positive charge, okay? And if you remember from heterolytic fission, okay, when the bond breaks and the electrons go to B, in this case, B becomes negative, A becomes positive. So the carbon-hydrogen bond that you see here, the electrons is being donated to the delocalized system, so that's negative. Negative plus positive, it cancels out neutral. That means your hydrogen leaves as a hydrogen plus ion, okay? And then you form your product. Now, we're going to look at a specific mechanism, which is the formation of, well, in the learning objective, it says formation of bromobenzene. Our example, we're going to use chlorobenzene. It is exactly the same, okay? So benzene reacts with chlorine or bromine in the presence of a catalyst. This will replace the hydrogen atoms on the ring by a chlorine or bromine atom, okay? So for the reaction of benzene, only substitution can happen. Right, for this reaction, you can carry out in room temperature, but with the presence of a catalyst. If you remember the reaction of alkenes with bromines or chlorines, they happen at room temperature in aqueous condition. There is no special condition for a reaction of alkenes and chlorine, aqueous chlorine or aqueous bromine, okay? For alkanes, it can also react with chlorine, but in the presence of UV light, okay? In the case of benzene, you need a catalyst. This catalyst is called the halogen carriers, okay? So what are these catalysts? It has to follow the reagent that you use. If you use chlorine as your reagent, your catalyst has to be anhydrous aluminium chloride. Now the anhydrous needs to be there. The moment you write down aqueous, it's wrong, okay? Because anhydrous means it's dry. So do not write aqueous aluminium chloride or aluminium bromide. Same thing, aqueous iron chloride or iron. So you can choose any of these three as your catalyst, or we call it a halogen carrier. Now, why does it work with iron? It's because when you have iron, and then this is your reagent, chlorine, iron chloride is being formed, and iron chloride is a catalyst, okay? So if you use bromine as your reagent, you will use anhydrous aluminium bromide or iron bromide, or you can react it with iron. The iron will react with bromine to form iron bromide, okay? So do not mismatch your catalyst and your reagent. If it's chlorine, then you have to use a halogen carrier of chlorine. Okay, now this is the overall equation, okay? The top one is for the reaction between benzene and a chlorine. The catalyst is an anhydrous aluminum chloride. Notice how they write down the anhydrous because that condition is important. If it's aqueous, automatically the reaction will not happen. Okay, so the product, you have chlorobenzene and hydrogen chloride. Later on, when we look at the mechanism, you will see how we form hydrogen chloride. Okay, if you use bromine as your reagent, your catalyst would have to be anhydrous aluminum bromide or iron bromide, and then you form a bromobenzene and a HBr. Okay, so let's go straight to the mechanism. The first step of the mechanism is the production of electrophile Cl+. Okay, so you started with the reagent chlorine, but the benzene only reacts with the electrophile. Okay, so what happens? Cl bond breaks. Okay, same thing. If I number this, Cl1, Cl2, okay, the electrons from the bond goes to Cl number 2, not Cl2, okay, Cl number 2. So that means Cl number 2 becomes Cl minus. Cl number 1 becomes Cl plus. Okay, this is Cl1. Cl2 becomes Cl minus, and it is combined with AlCl3 to form AlCl4 minus. Okay, so please take note of that 4 because chlorine number 2 is being added to a aluminum chloride, and chlorine number 2 gets the electrons, therefore chlorine number 2 becomes Cl minus. Okay, so the one that we're interested in, the species that we're interested in here is your Cl plus, which is the electrophile. I am loving this iPad actually. Okay, so Cl plus is our star of the show. Moving on. Okay, so what happens is that now we start drawing. Please make sure you copy this down in your notes. I am going to use blue. Okay, so first things first, you have your benzene ring. Okay, and then you have your electrophile, which is red in color, just because. So your delocalized electrons is being donated to the electrophile to form an intermediate with a broken delocalization system. Okay, I'm going to put my chlorine on that carbon just because. Okay, so if I number my carbon, wherever that chlorine is sitting is automatically number 1, 2, 3, 4, 5, 6. Okay, now on that carbon where the chlorine is sitting, carbon number 1, there is also a hydrogen. I don't know why I started. This should be red. I am having fun with this. Okay. Now, since your chlorine, your electrophile sits on the first carbon, your delocalized system is only between carbon number 2 to carbon number 6. Okay. I should move this up because I need some space. I hope you can see that. How do I make this smaller? Cannot. Okay, right. I am missing my positive charge, okay, because the positive charge was from the electrophile. Okay, of course, it has to go somewhere. Right, next step is to restore my delocalization. I need to cancel out that positive charge, and the only way for that is for the electrons in the carbon-hydrogen bond in carbon number 1 to be donated into the delocalized system. Okay, so now the delocalized system is negative. So negative plus positive cancel out. Okay, your H hydrogen, since it does not get the electron, it becomes H plus. You release it as a H plus. That hydrogen cannot sit there because each carbon can only hold one bond, one hanging bond outside. Okay, so that means your product is what we call a chlorobenzene with that chlorine there. Are you happy? Okay, there is an additional section where it says the regeneration of catalyst H plus. Your H plus will react with, let's see, if we go back to the previous page, well, in my case, it's a previous page, okay? So if you look at the production of electrophile just now, you have electrophile, which is Cl plus, and then you have AlCl4 minus, right? Okay, this other product, AlCl4 minus, is what we are going to use it to react with the H plus. Okay, this section is called the regeneration of the catalyst. Regeneration of catalyst. Okay, what happens is that the H plus from this step will react with AlCl4 minus from step 1. Okay, so you want to regenerate your catalyst. Your catalyst is AlCl3. That means your Cl minus from AlCl4 minus combines or go with H plus. Cl minus plus H plus is HCl. The other product is AlCl3, which is your catalyst. So please take note of that. Okay, basically the AlCl4 minus is giving away its chloride ion that it got from step 1 just now. The chloride ion combines with the hydrogen ion to form HCl. The AlCl4 minus now becomes AlCl3, and AlCl3 is the catalyst. And this is how you can show how a catalyst stays unchanged. Actually, it was changed for a bit, but then they go back to the original form. Okay, in the first step, you see the catalyst turning into AlCl4 minus. Then after that, it reacts with H plus. Ooh, okay. Any questions so far? Are we okay? Hello? Right, so then we move on. If no question, we move on. Is there anything that I want to add here? There is. Okay, let's just add. I'm going to type it out. Here it says benzenes delocalized system, delocalized ring of electrons is disrupted. Positive charge spread over 5 carbon atoms, which is from carbon number 2 to carbon number 6. I hope you can see that. Okay. Okay. How do I move this text? I can't move this text. So yeah, I really like this iPad. I might actually use this after when school reopens. Okay, are you done copying that? What's this? Oh. Ang, are you done copying? Okay. Next page. Next slide for me. Now we move on to methylbenzene. Oh, before I move on, sorry, was stretching. This mechanism works the same for bromine as well. Okay, so if you have bromine and then you just change everything to Br, this becomes Br plus, this becomes Br, you form a bromobenzene. And when we look at the previous one, if we are using Br, same thing, Br2 to react with aluminium bromide to form Br plus electrophile and AlBr4 minus. Everything else is the same, okay? Right, next. Methyl benzene. A methyl benzene is when you have a methyl group attached to the benzene ring, okay? Methyl benzene and other alkyl arenes can undergo electrophilic substitution and therefore be halogenated as well. So as long as there is a benzene ring, the mechanism will be the same, which is electrophilic substitution. Okay, so same thing. You would imagine. I'll show this later. Okay, so methyl or any other alkyl groups or alkane groups, when it is attached to benzene, it has this effect called electron donating group. Okay, so that means it doesn't really give away their electron, but just the electron density. They push some electron density into the ring. So you can imagine this ring is already an electron-rich region. Along with methyl donating its electron density, the ring will be even more electron-rich. Okay? So the effect of methyl or any other alkyl is that it activates carbon number 2, carbon number 4, carbon number 6. Now, the moment you have an alkyl sitting here, automatically that carbon becomes number 1 already. Okay, so position 2, 4, and 6 is activated. What do I mean by that? So let's have a look. Okay, I'm going to use pink because it's my favorite color. Okay, so here you have a methyl alkane. Here, okay, methyl alkane, sorry, methyl benzene. Okay, so if you have a chlorine with anhydrous aluminium chloride, so that means electrophilic substitution will happen. Okay, so the benzene ring, the delocalized system, the delocalized electron will attack the Cl plus electrophile, the same method as your benzene ring, okay, same mechanism, okay, but with the presence of an methyl group, only the position 2, 4, and 6 is activated. What do I mean by that? It means that my chlorine will sit on the second position, or the other possible product is the fourth position. Okay, now 2, 4, 6. The other possible position is 6. Do you notice that the 6th position and the 2 position is the same? You just flip your molecule. Okay? So this is what it means by activating the position. That means your electrophile will sit in position 2, 4, 6 with respect to your methyl group. Okay? Your methyl group will be number 1 here. Then this becomes number 2. Number 1, 2, 3, 4. This one is the same, so I will just erase them. Okay, carbon 2 and carbon 6 in this case is the same. There are some cases where they are not the same, so you have to think about the possible products. Okay, the naming has been given to you. One thing that you should be careful is that when you draw the mechanism, only the hydrogen is being released. You never release the CH3 group, okay? You do not break the carbon CH3 bond. That means your electrophile will never sit on the first carbon, okay? That is when you have limited amount or limited supply of chlorine. What if you have chlorine in excess, which is the in your notes, it's the bottom part, I think. It's the second. Yeah, hold on. Yep, in excess chlorine, okay? Even though you have excess chlorine, it will still be the 2,4,6 position that will be activated, okay? So your product will be, this time you have excess chlorine. I hope you can already tell the product. So, oh, ayo. What's wrong? Okay. So your product can be on the 2,4 position. The other possible product is a 2,6 position. Okay. What's the other possible product? Is when you have 2, 4, 6. Okay, so this happens when you have excess chlorine. Let me just number them first. That's 2, 4. Not a nice color. This is 2, 6. This is 2, 4, 6. Okay, when you have two substitutions happening at a time, we call it a di substitution. Okay, so this 2 is a di substitution. And then the last product is a tri substitution. Okay, that means you can substitute the hydrogen in the carbon 2, carbon 4, carbon 6 at one go. And this only happens with excess. Okay, naming. I'll just name one of the molecule. So this one is called, oops, this one is called 1-methyl 2,4-dichloromethane. Dichlorobenzene. Dichlorobenzene. Hope you can see. Okay, this is called 1-methyl 2,6-dichlorobenzene. This is called 1-methyl 2,4,6-trichlorobenzene. Okay, let me just highlight that because I like to play with the highlighter. 2, 4, 6. There's another 4,6. 4,6 is the same as 2,4. Can you see that? 4,6-dichlorobenzene is the same as a 2,4-dichlorobenzene. So the only possible products that you can get here are these three. Any questions so far? So this is a 2,6. Please change your name accordingly. This is a 2,4,6-trichlorobenzene. What about 3,5? 3 and 5 will not be activated. They will not sit on 3 and 5. They will only, good question, Ben. They will only sit on position 3, 5 if position 2, 4, 6 is blocked. For example, okay, for example, you have this structure. You have CH3, okay, and then it is attached with, say, C2H5, and then it is attached with something else, CH3 again, and then a CH3. So you can see that carbon 1, 2, 4, and 6 are blocked. Okay, then if you want to react this with Cl2 under the with the presence of a halogen carrier, which is anhydrous aluminium chloride, then only your chlorine will sit on position 3 and 5. Okay, so that's like your last resort, right? While your 2,4,6 is empty, your chlorine will sit on 2,4,6. Even in excess, they will sit on 2,4,6 and as well, unless you force them to a further reaction. But otherwise, you will just stop them at 2,4,6 position. Okay, that's a good question, Ben. Why is it only possible for last resort? Because you want the reaction to happen. Because you want the chlorine to go into the benzene ring. Here, you start with a methyl benzene, so the chlorine will go to 2,4,6 first. Unless if you leave the reaction to go on for very long, maybe the 3 and 5 position will be filled up. But even so, you know, we can't say for sure. Okay, even for this reaction that I was talking about, last resort, they may or may not happen. Okay, the bottom line is, if it is available, if it's empty, 2,4,6 will be filled in first. Okay, 3 and 5 may or may not happen because that positions are not activated. Is that okay for you? Right, moving on. So the bottom line is, when there is an alkyl group, whether it's methyl, ethyl, butyl, propyl, and etc., bonded to the benzene ring directly, then the 2, 4, and 6 positions are activated. Okay. We also say that this alkyl group is an electron donating group. That means it adds more electron density to your delocalized system. So your delocalized system is now even richer with electron density. Oops. Next page. How many minutes do we have left? How do I tell? How can I tell how long the session has been going on? Oh, I clicked the wrong button. Okay, right. Miss almost cursed. I know. The next learning objective is predict whether halogenation will occur in the sidechain or in the aromatic ring, depending on the reaction of the conditions. Okay, so as you all know, alkanes can react with chlorine under UV light. Okay, alkenes can react with chlorine with no special condition. Room temperature is fine. Benzene can react with chlorine in the presence of a halogen carrier, which is the catalyst, which is anhydrous aluminium chloride, as an example. Okay, so you can see that this different functional group can react with chlorine at different conditions. So you really have to read the question. What condition is being used here? Okay, so why do I talk about alkanes, alkenes, and benzenes? This is because, next page, in an alkene, in a benzene, like here, this one, a methyl benzene, there are two functional groups. One is the benzene functional group, or the arene, and the second functional group is an alkane. Okay, so that's why it is important for you to look at the conditions. Okay, all right, so I just got the 10 minutes warning, so we have 10 minutes left. So reagent is the same, chlorine or bromine, but the condition is different. Okay, if you have a halogen carrier, then obviously the reaction occurs in the ring. What does that mean? That means, okay, you either attach bromine directly on the ring, okay? That mechanism is called the electrophilic substitution reaction, because this is for benzene. So please write that down. Electrophilic substitution reaction. Okay, so this is the condition for benzenes or arenes. Okay, the next one is if you use the same reagent again, chlorine and bromine, but the condition is now different. UV light or heat. This condition is specific for an alkane. So the reaction happens on the side chain, on the alkyl group. If I just redraw this molecule, CH3, okay? This reaction is called a free radical substitution reaction. So what happens is the carbon-hydrogen bond on the side chain will be replaced with the halogen. Okay, so this is showing you the reaction on the side chain. Sorry, this is showing you the reaction on the side chain. This is showing you the reaction in the ring or on the ring directly. The mechanism is called free radical substitution. Okay, likewise for an ethyl, if we look at the ethyl benzene, same thing. If you use UV light, then it will not attack the ring. It will attack the ethyl group. Okay, there can be a mono substitution, di substitution, tri substitution, or you can substitute all the hydrogens if you still remember from your AS. Okay, the halogens will replace all your CH bond. You still remember this? Okay, let's see what's next. Oh, okay. So this question, if the chlorine gas is passed into boiling methyl benzene in the presence of UV light, remember that you have two functional groups here. One is the arene functional group, and then one is the alkane-ish, it's like an alkane functional group. So this condition, UV light will attack the alkane. Okay, so that means your product would be, if we just talk about mono substitution, okay, your product, your benzene stays the same. Your benzene stays the same. So your product is now CH2Cl. Just talk about one substitution, okay? Mono substitution. The other side product is HCl. And this is a free radical substitution. Please take note that there is no substitution in benzene ring, because this condition is only for alkane. So that is all for today. Tomorrow we will look at nitration of benzene. Okay, the mechanism will still be the same. It's just that the formation of electrophile is slightly different. Okay, any questions before we go? We have less than 5 minutes left. Hello?
No.
No question? I just want to highlight this chlorine. Okay. Okay, are you happy to go?